Hi, today I'm going to present our research GPGPU core in Alveo U200 card. So in order to do that, I'm just going to give you the Alveo U200 card specification here. So this Alveo U200 card is a data center card. It's very powerful in terms of computation and RAM and network interfaces. If you look at the specifications here, so it has a off-chip memory of 64 GB and then internal RAM capacity of 35 MB, and it is a PCI Express Gen 3 by 16 lane. So and then it has a lot of LUTs, so 892,000 LUTs. So basically the U200 card from AMD is very powerful for data center applications. So what I'm going to show you is that how we designed in Vivado, and then how to program it, and then how to run a test. So what we did was we have taken this is a Vivado IP of RacEr GPGPU. So you can see that the place here. This is RacEr GPGPU. So we have connected to XDMA DDR4 through AXI Smart Connect. So it's a AXI4 protocol. So you can see that the IP core here, AXI Smart Connect SMC. So this is the interconnect for DDR4. Then and then clock wizard as well. So once we connect it, and then you have to run synthesis implementation, and then generate a bit stream. So once we do that a bit stream, so then you open the hardware manager. For the demo sake, I'm just going to open the hardware manager here, and then open target, then auto connect. And then right click on XEU200, then program device. Then here you have to program the bit file what we provided you. So since I already programmed it, so I'm just going to cancel it here. Then you need to reboot the server. So once we reboot the server, and then you have to go to our directory. So I'm just going to show you the directory here. So you got to go to this directory, RacEr F1 regression CUDA, and then type make regression. Okay, so I'm just type it, make regression. So it will ask you the sudo password, then enter the password. So once you enter the password, it will run the regression tests. So these regression tests for a lot of computations, for example, integer addition, integer multiplication, shared multiplication, and then posit computation in addition, multiplication, and division, and so forth. So you can see that the regression tests are passing. So what we are displaying here is that maximum relative floating point error, in the sense that it is measured in terms of accuracy. So lower the error, better the results are. So for this, for example, for floating point addition, is a floating point addition. Okay, floating point addition is the maximum relative error of 1.164 into 10 raised to minus 7. It's pretty good for FP32 or P32 computation. So if you look at the source code, what we are doing is that, so this is our directory for the POSIT computation. So we look at this, it's coming from RacEr many core, RacEr CUDA time float vec addition. So if you look at this, the kernel code, kernel, and .c. So this is the code for posit addition and multiplication, posit addition. So what we are doing is we are calling a Fortran program here. So RacEr GPGPU supports Fortran C++. So in this Fortran adder, so what we are doing is we're just doing a basic floating point addition, and then calling this function from the Fortran. So I'll show you the code here. And so let's see. So this is a basic addition, floating point addition in Fortran. Then in the kernel, we are calling this function, and then these are the RacEr API calls. So what they're doing is group ID, grid ID, and grid dimensions. So and then we already pre-assigned for these dimensions here. Then it will call the contents in those grid. So then it will do the computation for posit addition in Fortran. Similarly, for the if you look at um, multiplication float like mul kernel. So what we are doing is we are doing a posit multiplication. Okay, so this is a posit A and B we are passing as an array A, B, and then C as a we are getting the result C. So this whole grid doing computation in posit, and what we are doing is that we are doing computation in posit, and then we are comparing the posit results with the floating point results. So how we are doing is that, so if you look at in the CUDA structure here, so it's a test float like it's add. Okay, so this is a x64 floating point addition, and then what we are doing is, so we are comparing floating point addition with the posit addition. So this the whole function calls the kernel. So what we shown you previously, this kernel floating point kernel floating point add c. This will call floating point addition add c. This function will call kernel float add. It will call that kernel. Then after calling, so we are testing regression for 1024 number of regression tests. Then we will initialize the memory A, B, C for the input and output in a RAM. Then we generate a random numbers here. So these random numbers are passed to the kernel. So you can see we are passing to the random numbers to the kernel A, B, C, and we are passing A as well as B. Then we reading result from C, and then once we reading results from C, then we are comparing accuracy. So both A, B, and C is the expected one, and so expected is from the it's a GPU C host is from the x64 or x86 machine. So and then this is what you're seeing the uh, maximum relative error. Okay. So if you wonder how the grid structure or how the API calls looks like, so you can visit our website here. Go to the website vividsparks.com and then click on resources and then click on programming guide. Then read more. Click on read more. It will open the programming guide, and then So, so all the CPUs, these are general purpose CPU connected in 2D mesh network, and these are the routers and DDR RAM of U200, and then these are connected to PCIe. The whole GPGB connected to PCIe. And these are the API calls. Um, then the whole grid structure looks like. So it's a 3D network. So and then so we slightly modified the original CUDA kernel. You can see the modified version and the original version side by side. You can verify it in the program as well as in the programming guide. You can help yourself, or you can ask if you need more information. Okay. Yeah. So okay, that's it. So if you need any more clarification, please do contact us. Thank you.